Swayam Prabha. Digital India. Educated India.
And how to solve for free electron under potential, and we also learned what is the effect when the potential energy or applied potential is more compared to the energy of electron. We get a exponentially decaying wave. When the energy of electron is more than the potential, we get a traveling wave, right? Why do we get a traveling wave? Because total energy is potential energy plus kinetic energy. So for traveling wave, your kinetic energy has to be positive, and when the potential U is more than the energy of electron, that means kinetic energy is negative, right? So that means you cannot have moving electron, right? So we get basically exponentially decaying wave. Okay, now let's consider a few examples that will help us to eventually understand how the electron in a crystal behave. So first of all, we will consider particle in a box. So particle in a box. So box is basically a potential box. So in the middle of the box, or from length 0 to L, potential U is 0, and at the boundary, potential energy is infinite, right? So if the energy is infinite, this electron cannot escape the well. So in this case, if you try to solve the Schrodinger equation, what will you get? You will get e to the power iota kx, right? That we have already discussed, right? So solution is very similar to the free electron, but only difference is the boundary conditions, right? So what is the boundary condition? When U is infinite, the probability of finding electron should be 0. So at x equal to 0 and at x equal to L, your wave function should be 0. So if wave function is 0 and this e to the power iota kx, you can write sine kx plus cosine kx, right? So the function that fits well here. So at x equal to 0, only the sine kx is 0. So it has to be only sinusoidal function, right? Because cosine is non-zero, so that coefficient has to be 0. So you can write a sine kx plus b cosine kx, right? So at k equal to 0, this will be b, but wave function is 0, so that means b has to be 0. Then at x equal to L, a sine kx should be 0, so kx equal to multiple of pi. So kl is n pi. So n can be 1, 2, 3, like that. So you will get multiple values of k, and those k you can denote as kn, k subscript n. So k1 will be pi by L, k2 will be 2 pi by L, right? So you will have number of solutions, and you can also plot those waveforms psi. So for k n equal to 1, you will get a half wave here, right? So nodes are at the two end and maximum is at half length. For n equal to 2, you will get one positive peak here, one negative peak here, and nodes at the two end. And interestingly, you also get a node in the middle, right? So probability of finding electron for the second node in the middle is 0, right? For first wave function, psi1 is maximum here, psi2 is maximum here, right? Psi3 is also maximum here, right? So this is the wave function, how it looks. So it tells us the probability of finding electron for a particular wave function. Now overall function, overall distribution of electron can be the superposition of these different solutions, psi1, psi2. So your actual psi can be, let's say, some coefficient a1 times psi1, some coefficient a2 times psi2, some coefficient a3 times psi3, and so on. Now when we normalize it, how do we normalize? We normalize psi star psi dx equal to 1. So by that we can get the coefficient a, and you have to integrate from 0 to L. So this will become a square sine square kx dl. Now integral sine square kx dl is how much? 0 to L. So sine square you can write as 1 minus sine theta can be written as 1 minus cos 2 theta, right? So that will be if you integrate 1, it will be L only, right? So let's say right sine square theta is equal to 1 minus cosine 2 theta divided by 2. So cosine 2 theta integral will be sine 2 theta, and that from 0 to L will be 0, and this will become L by 2. So a square is equal to a square L by 2 equal to 1, right? So that will give a square L by 2 equal to 1. So a will be root 2 by L. So this is a will be root 2 by L. And from this K you can also tell what is the energy of electron. Energy of electron is h bar k square by 2m. Now k is n pi by L. So you can write h bar square n square pi square by 2ml square. Right? So this will be the energy of electron. Now U is 0 here, right? So this is the totally the kinetic energy of electron. And overall you can write psi n is a root 2 by L sine n pi x by L. And this is the time e to the power minus iota omega t. This is basically obtained by writing E is equal to h bar omega, right? So you can include or not include, not necessary, but just to show you the whole solution, I have written it here. Okay. On the left side, you are seeing omega versus k. So you see here, this is h bar omega is equal to h bar square n square pi square by 2ml square, right? So or h bar square k square by 2m. So k is discrete and is uniformly spaced, right? So k1 is pi by L, k2 is 2 pi by L, k3 is 3 pi by L, and corresponding E is k square, right? So this relationship is parabolic. So what you have here, you have discrete energies, right? So there is a state here, there is a state here, there is a state here, right? Similarly, you have a state here, you have a state here, you have a state here, right? So this is basically minus k. Now k and minus k, what will be the difference? What is the meaning of minus k? So let's
Direction of propagation is opposite.
Opposite direction.
correct. But here, do we have a traveling wave? They are confined inside. They are confined inside, right? So this wave will actually not travel. Means in this potential well, they have option to travel, right? But due to boundary condition, what we will get? We will get a standing wave, right? So they will just oscillate basically. Instead of travel, they will oscillate. So wave will exist only inside this potential well, and they will oscillate, right? So here minus k, you can say it's a redundant thing basically here. Okay. Now physically, what is happening here? Now what is the operator for energy? What is energy operator for kinetic energy? Kinetic energy is h bar square k square by 2m, right? So k square you will get double derivative of wave function with respect to space position, right? So del 2 psi by del x square, right? So this double derivative will tell you the kinetic energy. Now let us consider. So if you look here, where the curvature is more, psi 1 or psi 2?
Psi 2.
Correct. And who has more curvature, psi 2 or psi 3? Psi 3 have more curvature, right? So you see, as the curvature is increasing, their energy is also increasing, right? So wave function that have smallest curvature they have less energy, right? So you can see here psi1 again here, and where is the this thing curvature? You see the curvature here is very smooth here, right? And this psi2 has a curvature here. Here it goes to 0, right? So, and another thing that you can see here, what is the derivative? So, what d psi by dx give you? D psi by dx gives you what?
Slope of a tangent.
It's h bar k, right? So it's momentum, right, or the velocity of the wave. So this particle, basically, if you assume a particle, it will move here. Here it's basically is stable, right? And here it's again moving, right? So from just looking at the waveform, you can draw so many conclusions, right? So now there is another concept you will probably learn in signal system. These waveforms are orthogonal to each other. So if you take the product and integrate it, right, they should average out to 0. Now the length of the box is L. If you squeeze the box and make length smaller, what will happen? Because its amplitude is root 2 by L, right? So if you squeeze the length, make it less, amplitude will increase. So that means curvature will also increase, and that means energy will also increase, right? So the spacing of different energies E1, E2, E3 will actually increase. So you can see that delta K will increase and delta E will increase. Now delta K will be proportional to 1 by L and delta E will be proportional to 1 by L square. Okay. So this also explains, if you localize the particle, right, it increases its momentum and energy, right? Correct? Okay. So this is okay. Now, if there is a non-zero potential inside the box, right, in the well, then equation will remain same. Only difference will be Kn will be replaced by E minus U here. Root 2m E minus U by h bar square. Now here E is the energy of the, what is the En? En is the energy corresponding to particular mode. So energy of electron, what is the requirement of energy of electron? Can it be less than E1? Yes,
More than
it cannot be less than E1, right? You can type here basically. You can type here instead of speaking. Please type here. So maybe 1 or 2% type, and I will say. So can energy be less than E1? No, right? Can energy be E1? Yes. Can energy be E2? Yes. Can energy be in between? So is more than E1, but less than, more than E1 but less than E2. Is it possible? Can the energy of electron be between E1 and E2? Okay. As I told you, psi can be a linear combination of
Sorry, I'm muted.
You're muted.
okay. So energy of electron can be anything between E1 to E2 or any number in between, right? Why? Because this wave function is the linear combination of individual wave functions. So overall wave function can be a combination of different wave functions, right? So its energy need not be exactly E1 and E2, those discrete energies. It can be combination of those. The only difference is that it cannot be less than E1, right? Because there is no mode corresponding to energy less than E1. So energy has to be more than E1, and it can take any energy in between if the wave function is a combination of different modes, basically, right? But if you consider individual modes, then their energies are discrete. Okay. Now, third case, again here inside the well, potential energy is 0, but the barriers are not infinite, right? So now you have finite energy barrier here, and we call it finite potential well. In this case, how will you solve? Here, now at x equal to 0 and x equal to L, psi need not be 0, right? Psi need not be 0. Instead, what condition we will use? Psi at 0 plus is equal to psi at 0 minus psi at L plus is equal to psi at L minus. You remember the postulate that psi wave function is single valued, continuous, right? No jumps, and this is a property of its derivative also, right? Its derivative also single valued and continuous. So you can also write psi prime or d psi by dx, you can say, at 0 plus is equal to d psi by dx at 0 minus, and same thing is true at L plus and L minus, right? So now you have 4 equations. Inside the well, you can write a sin kx plus b cos kx, right? That we already know. Outside, there are 2 possibilities, right? Energy is more than U net, then wave will be traveling. So you can use either. If energy is less than U naught, then it will be exponentially decaying here. So let's say this is a case corresponding to energy less than U naught. So wave function you can write e to the power minus alpha x, right? Where alpha is because here we define k prime as root 2m e minus u naught by h bar square. So whole thing is under root. So alpha will be, because e is less than u naught, right? So alpha will be square root of 2m u naught minus e by h bar square, right? So e to the power minus alpha x. Similarly, on back here, it will be e to the power alpha x, right? You can write, let's say, coefficient c here and d here. Now why alpha x here? Because here x is negative, right? So it has to decay, right? It has to decay here. So now you can use the boundary condition at these 2 positions, x equal to 0 and x equal to L, and match psi and d psi by dx, right? You notice here some of the wave function is going through this barrier. So although energy of electron is less than the potential, right? Still these electrons are able to penetrate. Please remember, these electrons are able to penetrate, but they are not traveling wave, right? They are not traveling. They are just penetrating and decaying. Correct? But let's say this potential was small, right? Its thickness was less. Then if penetration is more than the barrier thickness, then we will have tunneling. So outside this, again they will propagate, because outside this energy may be less than the potential energy u naught, may be less than the energy of electron, right? So that is called tunneling. So in tunneling we have traveling waves basically there, and just a thick barrier we have waves decaying here. And sometimes they are called evanescent waves. Okay. So we will solve this one particle at a step. So previous question you can try. Maybe you can try it as homework, but it's very simple. So here you will have a sin kx plus b cos kx, c to the power minus alpha x in region 2. This is region 1. And in region 3, you have e to d times e to the power alpha x. You have 4 variable a, b, c, d. And then you have 4 equations. Psi d psi by dx x equal to 0. Psi d psi by dx x equal to L. So you can calculate these 4 variables, 4 coefficients. Okay. Now let us say if there is a wave traveling here, right, or electron with certain energy E, right, is coming from left to right, right, and it encounters a potential barrier whose height is u naught, and there are 2 possibilities, right? E is more than u naught, E is less than u naught, right? What will happen? Can you visualize the picture? If energy of electron is more than u naught, so classically we will think that because energy is more than the potential barrier, electron will pass through, right? The only thing will be here, this is the kinetic energy. So because u is 0 here, so E is the kinetic energy. Here kinetic energy will be E minus u naught, right? And if energy is less than u naught, electron will be reflected, right? Nothing will penetrate here, right? This is what classically we think, right? But if you look at it, look at the problem from Schrodinger equation perspective, we can consider a general case. So in general case, there is a wave traveling to right, and let's assume its amplitude is unity, right? Or if amplitude is anything, we can always scale it, right? So assume it's unit amplitude. So you can write e to the power iota kx, right? So wave coming here is e to the power iota kx. Now wave reflected, let's say reflection coefficient is r. So r times e to the power iota kx. But now this is traveling in minus x direction, right? So you will have minus iota kx here. Now please remember, or please keep in mind, the time dependence is always e to the power minus iota omega t, right? Right. So this what is always there. Right? We are not explicitly writing it, but it is there. So basically, wave traveling in positive x direction, e to the power iota kx minus iota omega t. Wave reflected is e to the power minus iota kx minus iota omega t with coefficient r. And then some wave is transmitted, so that we can write, again it's moving in x direction, so it's e to the power iota kx times t, right? So you can write 2 waves. For x less than 0, incidence wave plus reflected wave. For x more than 0, you have transmitted wave, right? Now k is different. For region x less than 0, k is root 2 me by h bar square. For region x greater than 0, we call it k prime, and k prime is root 2m e minus u naught by h bar square, because its kinetic energy is now e minus u naught. If E is more than u naught, you have positive kinetic energy. If E is less than u naught, you have negative kinetic energy. That means wave will not propagate. Correct? And again, you can use boundary condition at x equal to 0, because psi and its derivative are continuous. So psi at 0 plus and 0 minus, they are equal, and derivative of psi at 0 plus and 0 minus are equal. So can you write at psi equal to 0? This will be 1 plus r, right? And for x equal to 0, this is t, right? So 1 plus r equal to t. What are the derivative? So derivative will be k. This will be minus k times r. So minus rk is equal to k prime times t. Because iota is common, we can ignore it. So you can write it k times 1 minus r is equal to k prime t, right? So now you have two variable r and t and two equation. We can obtain the value for r and t, right? You can do it here. If you take k to other side, you have 1 plus r divided by 1 minus r. Just take that, you divide equation 1 by equation 2, right? So 1 plus r by 1 minus r is equal to t will cancel, and at bottom you have k prime, and this k comes to this side, it will go here, so it will be k by k prime. So 1 plus r by 1 minus r is k by k prime. So r you can write this, this very familiar expression, 1 plus x by 1 minus x is equal to something. So x will be subtraction k minus k prime divided by k plus k prime, right? So 1 plus r minus 1 minus r, that is 2r divided by 2, right? So it will be r, correct? So this is what I've explained. So from this you can get r is k minus k prime by k plus k prime. Similarly, you can obtain t is 1 plus r. So this will be 2k by k plus k prime, right? And k and k prime are the wave vectors in the two regions. So when energy of electron is more than the potential, both k and k prime are real. So you are propagating waves, right? Now, please remember, when we call about transmission or reflection, we deal with the current density or flow of the charge, right? The flow of the charge is not just psi. It is psi times velocity. And what is velocity? Is related to k, right? So reflection coefficient will be k times r by k times incident wave, right? Correct? And transmission coefficient will be, now for transmission it is k prime, right? So k prime t by k times 1, right? And square of this thing, right? So because for reflection k is same, they will cancel out, you have r square. So the reflection coefficient is r square. Transfer coefficient is t square, right? Times k prime by k. So you can understand like this, eh? Velocity is h bar k by m, and k is del by del x, right? This is a velocity operator, psi star psi, right? So so this is average velocity, right? Then this you have to multiply by the number of carriers, right? So that is psi star psi. So psi star psi is, so velocity times charge, right? So this is basically k, right? So this k is actually not squared, only this other part is squared, right? So this k will cancel out, you have r square here. Then k prime by k, you have t square here, right? So reflection coefficient is k minus k prime by k plus k prime whole square, right? And transmission coefficient is k prime by k times 4k square by k plus k prime square, right? So it becomes basically 4k times k prime. Sometimes in textbook they use other technique also, because if they don't want to tell you there's a velocity here, what we do, we call this as a reflection coefficient, right? So transmission will be 1 minus reflection, right? So if you subtract it, you will get 4k k prime by k plus k prime whole square. This you will not get if you write this as simply t square, right? So you have to take into consideration k prime and k also. Okay, value of j again. Okay, let me write here. Now j is what? Velocity times concentration.